Thank you, Vitaly. Well, I'd like to thank the organizers. It's good to see everyone again after the pandemic. Most of you who I know, I don't think I've seen since before. So anyway, yeah, so let's talk about single recurrence, which is not as fashionable as multiple recurrence, but how does it connect to, I should probably say, how does it connect to nilpotent structures? Well, the main questions about these things are, in some sense, how is single recurrence controlled by the Kronecker factor or controlled by group rotations, which of course are at the lowest level of nilpotence. So anyway, okay, let's get started. So let's work in countable abelian groups and talk about upper Banach density in countable abelian groups. And if you have a set of positive upper Banach density, you want to understand the structure of the different set of this set. And it turned out, it's been known for quite some time that Bohr neighborhoods are closely related to the sort of large scale structure of these different sets. So in general, in a countable abelian group, you define a Bohr neighborhood by taking a d-dimensional torus, a homomorphism from your group into that torus, and an open neighborhood of the identity in the torus or the zero in the torus. And your Bohr neighborhood is just what you get when you pull back that open neighborhood through the homomorphism. So these are easy to understand. It's easy to compute with Bohr neighborhoods. And so they're natural things to look at in additive combinatorics. And Bollner proved, 1954, that if you have a set of positive upper Banach density in an abelian group, and you look at the different set of A, then that different set almost contains a Bohr neighborhood. There's an small exceptional set of zero Banach density. And Bohr neighborhoods themselves have positive upper Banach density. So this is non-trivial. This is telling you some structural information about the different set. And it would be great if you could eliminate the exceptional set, because it's so easy to compute with Bohr sets. If you could eliminate that exceptional set, you would basically know everything about different sets of positive density. And Ruja asked this question explicitly, but I think the question was sort of around before then too. In any case, so can you eliminate that set? And as a consequence of Kriej's construction, Kriej was actually answering a slightly different question, and I'll get to that in a bit. But Kriej proved that there is a set of positive upper Banach density in the integers whose different set does not contain a Bohr neighborhood of zero. And I want to emphasize sort of natural questions related to what's known. Since we have examples like this, I think it's a good idea to try to classify these examples. This problem, I am proposing that this is a good problem to work on. This may be, and I think this is probably out of reach with current methods, but it's worth thinking about anyway. Pardon me. So, okay, there's Bohr neighborhoods of zero. Kriej's example does not eliminate the possibility that there's a Bohr neighborhood of some other number. So Bohr neighborhood of another number is just a translate of a Bohr neighborhood of zero. And so Ruja and Ruja's co-authors and I over the years have asked whether, if you have a set of positive upper Banach density, does it contain a Bohr neighborhood of something. And I constructed an example, a counterexample. And this problem, I think, is closer to what's doable now. Maybe if I convince a bunch of you that this is a good problem to work on, we can make some progress. I mean, it's probably still very difficult, but I think it's worthwhile to try to classify the sets of positive upper Banach density whose difference set does not contain a Bohr neighborhood of any integer. Okay. Yes. Yeah, so I mean, yeah, so you want me to actually be careful about the quantifiers in these statements? Yeah. So right. So okay, first of all, upper Banach density in the in a general group. Do you want me to write down Fulner sequences? I mean, just the supremum over, right? Supremum over the density with respect to a Fulner sequence. Yeah, any Fulner sequence. Yeah, and it doesn't really matter which specific Fulner sequence you take. It's the other thing is so for quantifiers. So yeah, so for the example here is for every D, A minus A does not contain a Bohr neighborhood of rank D, right? It contains no Bohr neighborhood at all. So, okay, and I want to try to sort of explain the core portion of these constructions. These constructions are all the same. So Chris's example and my example, I mean, somehow they're different in an important way, but the sort of finite building blocks that show up in these are all the same. And there's this finite model that captures the combinatorics really well. So here's a finite analog. So let's work in vector space over F2. You got your standard basis. E here is just the standard basis in F2 to the D. Subgroups in F2 to the D, which of course are also subspaces, form the, they play the role of Bohr neighborhoods. And so the sort of finite analog of Kries's example is if you fix K and delta less than 1/2, then for every sufficiently large D, there is a subset in F2 to the D of density delta such that A minus A does not contain any coset of any subspace of codimension K. Is that right? Does that seem like a reasonable statement? Somehow when I read it from here, it's harder to tell whether it makes sense on the screen. So anyway, okay. But here's how you can try to construct such a thing, try to construct such an A. These examples will be defined as, this A will be defined as a certain kind of Hamming ball. So you just define the usual Hamming weight of an element of F2 to the D, thinking of it as a string of zeros and ones. So W of X is the number of non-zero entries. The Hamming ball of radius K around an element in F2 to the D is just all the points that differ from Y in at most K indices. And so it might be nice to observe that the Hamming ball of radius K around 0 is 0 together with the basis plus the basis, and so on up to sums of K elements from the basis. Okay, so we're going to use this to construct A. A will actually be a Hamming ball of radius close to D over 2. Okay. And so I claim that in F2 to the D, if you look at the Hamming ball of radius K around 1, that Hamming ball intersects every coset of every subspace of codimension K. And when delta is less than 1/2 and D is large enough, the Hamming ball of radius K around 0 has density close to 1/2. And the difference set, AK minus AK, is disjoint from this Hamming ball around 1. So together 1 and 3 imply that AK minus AK, that difference set contains no subspace of codimension K, because if AK minus AK did contain a subspace of codimension K, then it would have non-empty intersection. That coset contained there would have non-empty intersection with the SK. So the AK minus AK would have non-empty intersection with the SK. So 1 and 3 together tell you that AK minus AK does not contain a coset of a subspace of codimension K. Yeah. And then the statements 2 and 3 I won't prove on the screen. I'll just say verbally. If you think about what the what these Hamming balls are, this is all strings of zeros and ones with just under, where you're allowing just under D over too many ones to appear in your string. So if you think of it in terms of random construction or coin flips, you can see, yeah, or binomial estimates is probably the right way to look at this. Your cardinality of this Hamming ball is going to be really close to 1/2 the ambient space. And 3, why 3? Well, you can see if you subtract 2 elements in this Hamming ball, you get something in the Hamming ball. You get something in the Hamming ball of radius D minus 2K around 0, and that's clearly disjoint. It's easy to check that's disjoint from the Hamming ball of radius K around 1. Okay, so how do you prove 1? And it's kind of cute. So this property is translation invariant because we're talking about cosets here, right? So you can actually check that the same property is true for the Hamming ball around 0. And meeting every coset of every codimension K subspace is the same as if for every surjective homomorphism onto F2 to the K, rho of H of 0K is equal to F2 to the K, right? If you meet every coset of a subgroup, then your image and the quotient is everything, right? So, but that condition is easy to check because you know rho of E spans F2 to the K. And we also said on the previous slide, the Hamming ball of radius 0 around K is just 0 union E plus E, and so on up to however many sums you're looking at. And so this rho of E is a spanning set in F2 to the K because rho is surjective and rho of E spans F2, rho is surjective and E spans F2 to the D. So you have a spanning set, rho of E, and you've got the appropriate number of sums here to cover everything in F2 to the K. Make sense? Now you know the Krige example. Or you know the important sort of combinatorial core of the Krige example. Everything I want to ask that I'll ask about recurrence properties is really asking some aspect of this question. Is there a fundamentally different way besides this? Is there a fundamentally different way to construct dense sets whose different sets lacks some prescribed structure. Anytime you see an example in the literature of a dense set whose difference set does not contain this or that, it's probably based on this kind of construction. And I don't know if you could classify, right? If you could classify the subsets of the dense subsets of F2 to the K or F2 to the D, whose difference set does not contain a coset of a subspace of codimension K, you'd be doing, you'd probably be able to answer most of the open questions about single recurrence. Okay, so now I actually want to go on and, now I want to go on and talk about Katz-Nelson's problem. So the combinatorial version of Katz-Nelson's problem, which some people can squint really hard at this paper by Veach from 1968. Jonathan mentioned this this paper in his mini course talk, but people say that this question is in there. This question is explicitly in Landstat, Ruja, Glasner, and Katz-Nelson. It's now known as Katz-Nelson's problem. And the question is, if you have a countable abelian group and a synthetic subset of that group, must the difference set contain a Bohr neighborhood of 0 in the group? And the answer is unknown. There's no countable abelian group for which the answer is known. I'm going to try to look at some examples in F3, the countable vector space over F3, and see if you can say anything interesting there. But anyway, these questions about different sets, of course, are related to recurrence and dynamical systems. So the standard sort of correspondence principles let you rephrase these questions about different sets in terms of these return time sets. And so let's put up definitions about that. Okay, so let's say we want to understand single recurrence in various categories of dynamical systems. So here's the standard definitions. A set, let's see, if you have a countable abelian group and a subset of the group, you say it's a set of measurable recurrence if for every measure preserving system and every set of positive measure in the system, there is a G in your set that brings the set of positive measure back to itself. Topological recurrence is the same, except now you're talking about minimal topological systems and open sets. And Bohr recurrence is the same, but now you're talking about minimal group rotations and open sets in the phase space, open sets in the group. Okay. It's not completely obvious from this definition that measurable recurrence implies Bohr recurrence, but once you realize that in a minimal system, every invariant measure has full support, then you see this open set here has to have positive measures. So you can see then that if S is a set of measurable recurrence, it has to be a set of topological recurrence. And if S is a set of topological recurrence, it has to be a set of Bohr recurrence. That's straightforward from the definition. And of course, the natural questions are, can you reverse these implications? The first explicit question as to whether you could reverse this implication in this exact language was asked by Vitali in 85, I think. And but it turns out Furstenberg had asked the same question in different language, and Ruja had asked the same question in different language. It wasn't realized until after the question was solved, I think, that these were all somehow the same question. Whether the second implication can be reversed is Katz-Nelson's problem. Okay, let's look at a couple of examples just for fun. Okay, so that's just the definition of measurable recurrence again. And so if you have an infinite set then, you know, if you take all the differences, the non-zero differences from that set, that forms a set of measurable recurrence. That's Poincaré's recurrence theorem. And the integers, of course, probably the most famous example of a set of measurable recurrence, and this kind of kicked off the study of sets of measurable recurrence as such. The perfect squares are a set of measurable recurrence due to Furstenberg and Charcouzy. Floor end of the 5/2 is a set of measurable recurrence as well. I'm not sure exactly who was the first person to point this out. Bosher-Nitzan, maybe? Probably known before. I don't know. Mate? Was it you? Yeah. 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 Anyway, what's that? Okay. Yeah. So, non-examples. N squared plus 1, not a set of measurable recurrence. It's not a set of Bohr recurrence because it's not recurrent for the group rotation on 4 points. It's a little bit harder to see why n factorial is not a set of measurable recurrence, but it turns out there are circle rotations for which n factorial is not a set of recurrence. So it's really not a set of Bohr recurrence either. Okay. And another way to phrase that same question I asked before is there some common structure underlying all sets of measurable recurrence? The examples seem to be very different, right? If you look at all the known examples of sets of measurable recurrence, there doesn't seem to be any common structure apparent to all the examples, but I don't really have a feeling one way or the other about that, but it's sort of a useful perspective. And you can ask the same for other recurrence properties too. Okay. So let me explicitly say what Kriej's example is about. So Kriej, as I mentioned before, Bergelsen, Furstenberg, and Ruja asked, all in different language, is every set of topological recurrence a set of measurable recurrence? And Kriej constructed an example of a set E, or no, just a set, which is a set of topological recurrence, and not a set of measurable recurrence. And actually, if you stare at his proof, you will realize that he actually proved this. If E is an infinite set, then in the integers, then there is a subset of E minus E, which is a set of topological recurrence, but not measurable recurrence. And that's interesting because you know this E minus E itself is a set of measurable recurrence. And that's one of the reasons this is interesting. This is only implicit in Kriej's original article, but I have a preprint where this is explained explicitly. This preprint here, separating topological recurrence from measurable recurrence, is essentially a rewrite of Kriej's original article. Hopefully, it's readable enough to understand Kriej's argument. Anyway, so now that you know there's a set of topological but not measurable recurrence, you might wonder what measure preserving systems can realize this kind of example. And so you might ask, what can you say about an ergodic measure preserving system admitting a set of positive measure that never comes back to itself for every n and a set of topological recurrence, Bohr recurrence? In other words, can you do the Kriej example where the non-measurable recurrence is realized by, say, a distal system or by a weak mixing system? Seems kind of likely that if you have a set of topological recurrence, it also has to be a set of recurrence for distal systems. But I'm pretty sure you can do the Kriej example with a weak mixing system. So you can find a set of topological recurrence, which is not a set of measurable recurrence for some weak mixing system. Sort of a related question in that direction. Can you prove that if you have a set which is a set of recurrence for every measurable system having zero entropy? So just restrict the definition of measurable recurrence to quantify only over systems of zero entropy. Is that set a set of actual measurable recurrence? Right. Of course, this is getting at this sort of general idea of like, what can you find a class, easy to describe class of measure preserving systems that somehow captures all the information about what it means to be a set of recurrence. Okay. Now I'm getting at the things I wanted to actually show you that I'm kind of excited about. Yeah, measurable versus topological recurrence in other groups. So I'll say FP omega is just the countably infinite vector space over the field with P elements. Turns out Forrest actually constructed examples of topological but not measurable recurrence in F2 omega. And these examples can be lifted from subgroups and from quotients. So the Kriege example and Forrest example here resolves this question about topological but not measurable recurrence in a lot of groups. But it turns out whether you can do the Kriege example in F3 omega is still open. Yes. So yeah, I mean, that's an instance of what I was saying. All these examples have the same sort of combinatorial core, but it's true. So Forrest's example in F2 omega is very, very much the same idea as Kriege's. But there's still other technicalities. There's a lot of technicalities left out of that finite example. And anyway, okay. This I think is kind of an exciting problem. If you have a set of measurable recurrence, can you find a subset which is a set of topological recurrence and not measurable recurrence? Now I assert, and I will write up with Sohail that this is true for the perfect squares. That in the perfect squares you can do the Kriege example essentially, and other familiar explicit examples. But yeah, so in I already have, as a consequence of a construction answering a problem, a more intricate problem of Nikos and Emmanuel and Mate. As a side effect of that construction, I ended up with a subset of the perfect squares, which is a set of Bohr recurrence, but not measurable recurrence. So that's sort of strong evidence that you can do this. But for a completely arbitrary set of recurrence S, it seems very difficult to answer this question. It's very hard to get your hands on subsets, recurrence properties and subsets of an arbitrary set of recurrence. And you can ask the same thing, any other pair of recurrence properties you can ask, is there this sort of hereditary separation? Okay, so here's Katz-Nelson's problem phrased in terms of recurrence. So, like I said, there are people who believe Veach asked this question in 1968, but it was reiterated and now is known as Katz-Nelson's problem. Okay, so what is there? There has been some progress lately about Katz-Nelson's problem, and I want to say, Kunin and Rudin, as far as I know, were not aware of Katz-Nelson's problem, did not write about recurrence, but they did prove in this paper called lacunarity in the Bohr topology that if you have a lacunary subset of the integers and a subset of its difference set, which is a set of Bohr recurrence, then S is actually a set of topological recurrence. So that's already a non-trivial fact about Bohr recurrence and topological recurrence, because we know this E minus E here is a it itself is a set of measurable recurrence, and we know Friesia's construction tells us that it contains a set of topological but not measurable recurrence. So this statement here is not completely trivial, and seems to be saying something interesting. But yeah. Oh, well, okay. Was like, so lacunar in a general abelian group. So the real secret structure here is that lacunary sets are I0 sets. An I0 set in the integers is one where every bounded function can be uniformly approximated by a trigonometric polynomial. And so that can be defined in any, and exists in any countable abelian group. So that's really what they proved. They didn't state. For some reason, they said lacunary, but they talk about I0 sets in the paper, and they really prove this for, I mean, they really proved this. I just wrote it up in the language of recurrence in this paper in 2023. Anyway, yeah, does that make sense? But yeah, so it's about I0 sets somehow. If you could extend it to C, if you could replace I0 here with C-Don, then you would know it, or you would know the whole conjecture. Anyway, okay. In terms of special dynamical systems, Post, Craw, and Moss proved that if S is a set of Bohr recurrence, then S is a set of topological recurrence for minimal nil systems. But if I understand right, you actually get measurable recurrence. Is that right? For nil systems. So that's interesting. And Florian and Andreas and Daniel Glasscock in this survey, they proved that if S is a set of Bohr recurrence for if S is just a set of Bohr recurrence, then S is a set of recurrence for a special class of minimal skew product systems, instead of topological recurrence, I should say there. And so these things are all evidence that the statement, right, every set of Bohr recurrence is a set of topological recurrence is true, but I'd say it's not strong evidence. I don't know. This is a really nice survey. This sort of survey is like the whole history of Cass-Nelson's problem. I highly recommend it. Okay, so I want to give some explicit examples of sets of Bohr recurrence where I don't know whether they're sets of topological recurrence or sets of measurable recurrence. And so I want to do this in countable direct sum of Z mod 3Z. But let me just reiterate the definition of Bohr neighborhood here. So you get a Bohr neighborhood by taking a homomorphism into T to the D and looking at an open set around 0 and T to the D, and you look at all the G, all the elements of your group that are mapped into that neighborhood. That's your Bohr neighborhood of 0. And it's easy to check that S is a Bohr, it's easy to check that S is a Bohr neighborhood of 0 if and only if S intersects, or sorry, S is a set of Bohr recurrence if and only if S intersects every Bohr neighborhood of 0. And so if you're working in a group, a torsion group, like countable direct sum of Z mod PZ, then the Bohr neighborhoods of 0 are exactly the finite index subgroups, because, well, when you have one of these groups, the image, all the elements in this group have order P. Let's just say P is prime. All the elements of the group have order P, so all the elements in the image have order P. There's only finitely many elements of order P in the d-dimensional torus. So you're really looking at, when you look at these homomorphisms, you're really looking at a homomorphism into a finite group. So the Bohr neighborhoods of 0 are just the finite index subgroups in FP omega. Okay. And so what does this mean for being a set of Bohr recurrence in FP omega? Well, another way to say it is if S in FP omega is a set of Bohr recurrence, if for every D in N and every homomorphism from FP omega into a finite group, there exists a G where rho of G is equal to 0, and G in S where rho of G is equal to 0. So you can sort of forget about the neighborhood. You're just going straight to 0 in the definition of Bohr neighborhood for these groups. Okay, so again, we'll set up the standard basis E1, E2, E3 in F3 omega. Well, script E will be that basis. And it's not a set of Bohr recurrence because there is a homomorphism from F3 omega to F3 that keeps the image of E away from 0. Just the sum, the homomorphism defined by taking the sum of the coordinates, that maps the standard basis to 1, not to 0. So it's not a set of Bohr recurrence. On the other hand, if you look at elements of Hamming weight 3, in other words, you look at elements with 1s and 3 entries and 0s everywhere else, the set of such things forms a set of Bohr recurrence in F3 omega. And you can just pigeonhole to see why that is. So if you take a homomorphism from F3 omega to a finite group, you can just choose I, J, and K so that rho of EI and rho of EJ and rho of EK are all the same. And then rho of EI plus EJ plus EK, what is that? That's rho of EI plus rho of EJ plus rho of EK. That's 3 rho of EI, because said these are all the same, so that's just 0. And characteristic 3. And this EI plus EJ plus EK, I should say choose I, J, and K distinct, naturally. And this EI plus EJ plus EK is, of course, NE3. So that checks that your E3 is a set of Bohr recurrence. Now you might wonder which subsets of E3? Which subsets of E3 are sets of Bohr recurrence? Yeah. No, I mean, this is the most interesting part of the talk, so I figured I'd give you a second to think about it. Okay. So but to answer this question, we'll say, let's look at a collection of subsets of the natural numbers. We'll say F is partition regular if for every partition of the natural numbers, there is an element of the collection contained in one cell of the partition. And now you can sort of see that this is relevant to this pigeonholing idea here. So if you basically repeat the pigeonholing argument with the definition of partition regularity in mind, you get this characterization of Bohr recurrence for subsets of E3. So if F is a collection of 3 elements of subsets of N, and of course, these can be used to parameterize the subsets of E3. If F is a collection of 3 element subsets of the natural numbers, I'll just say EF is the things you get by adding up the corresponding basis vectors from indices in the elements of the collection. This is a set of Bohr recurrence in F3 omega, if and only if the collection F is partition regular. So, So that means you can look at lots and lots of examples of sets of Bohr recurrence. Who are these people? Ken Cunin is a big time set theorist you've probably heard of, but he did some work in harmonic analysis, and Givens was his PhD student. She did this in her thesis, and they co-authored a paper about this. They were studying the question of, if you look at the Bohr topology on 2 different groups, are those on 2 different countable groups, are those topologies homeomorphic as topological spaces? And that's why they're interested in this. Anyway, So of course you can look at this set. I'll say this. You can look at this set S sub 3AP, right? Just all the things with ones appearing evenly spaced in F3 omega. Or you can look at the corresponding configurations for Schur triples. And these things, this S sub 3AP is a set of Bohr recurrence in F3 omega. Is it a set of topological recurrence? If not, that answers Katz-Nelson's problem in F3 omega. Is it a set of measurable recurrence? Well, if S sub 3AP is a set of topological recurrence, but not a set of measurable recurrence, then I think that's something that separates topological recurrence from measurable recurrence in a way that's fundamentally different from the Krige example. I think this would answer that question. Can you find a fundamentally different way of constructing dense sets whose different sets like structure? Anyway, so the other reason it's interesting to look at this E3 set is because it turns out if you resolve Katz-Nelson's problem for subsets of E3, you have resolved it in general. So I proved in this paper, it's in Monnet-Schefte, I guess. If every subset of E3, which is a set of Bohr recurrence, is also a set of topological recurrence, then every subset of F3 omega, which is a set of Bohr recurrence, is a set of topological recurrence. So if you want to resolve Katz-Nelson's problem in F3 omega, you need only look at subsets of E3. And so somehow these kinds of things are interesting. I have no idea. I've not been able to resolve this for any non-trivial example. E3 itself is actually a set of measurable recurrence, but the proof of that isn't terribly interesting. So, okay, here's one more example that appeared at one point. Nikos and Randall McCutcheon asserted that this set is a set of Bohr recurrence. I don't know a proof myself, but in any case, this is an interesting question. So k factorial times 2 to the n times 3 to the m. This could be it. This could be an example of a set of Bohr recurrence that's not a set of topological recurrence, or it could have some other interesting recurrence properties. I don't know. Okay. I only have, what, 1 minute? Yeah, I'll take a minute. Okay. No, I won't. I'm going to stop there. Okay. Yeah, so Bohr recurrence, if you want to think of it in terms of different sets, S is a set of Bohr recurrence if for every Bohr neighborhood of an integer in, or whatever, yeah, Bohr neighborhood of an integer, the different set of that Bohr neighborhood intersects S. So the usual definition of Bohr recurrence is somehow the same as talking about different sets, and it's just different sets are usually not mentioned in the definition because every Bohr neighborhood of 0 contains a different set of a Bohr neighborhood. So when you're talking about Bohr neighborhoods of 0, you really are talking about different sets. Mhm. Why? Yeah, no, it's the same question. Yeah, it does, but but they can still be weak mixing, right? There are like weak mixing synthetic sets that are just totally uncorrelated with subgroups in F3 omega because it's an infinite group. So you still have weak mixing, like weak mixing actions. You have mixing actions. There's Bernoulli actions. Yeah. But it doesn't contain, they still don't contain cosets of finite dimensional. They still don't contain finite index subgroups. Yeah. Oh yes. Oh yes. Yeah. There you go. Yeah, I got it. Yeah. Thank you.